All right, so we're going to delve into the theory behind this, and unfortunately, I couldn't finish it. I mean, I think I was at 120 some slides already, and I said, okay, I'm going to do as much as I can today, and then next week I'm not here, so you'll finish up the you know, you don't have to come in. I know you commute from far, so you could actually just
I'm dependent on somebody else's schedule.
right. So you guys could work together here, and then you can either hold on to it for one more week or turn it in under my door. But so we're gonna have a little break before I actually go through the entire theory. But the purpose is when we look at a PDE, it's sometimes valuable to look at very specific solutions, as we already know because we've actually computed them and generated solutions and graphed them. So from beginning to end, we've seen the development of at least one of these specific solutions. But what's interesting about these solutions is they really reflect the symmetries in the structure of the PDE. So for example, if you look at Laplace's equation, you're looking at rotational solutions. Or when we were looking at the heat equation, we definitely were looking at radial solutions. And I didn't do this, but you can actually transform that into polar coordinates and really see the circle solutions on those PDEs. It's really neat. So we also looked at the wave equation and translation invariant solutions, which would make sense, right? If you have a wave, it would be translation invariant at the speed of the wave. So that makes absolute sense. We looked at dilation scaling in the heat equation. That's what we were doing when we were scaling out by 1 over square root of t to the 1/2, or 1 over square root of t. But how do you, like, without actually just guessing and testing, how do you look at this systematically? So you can find all the invariant symmetries at once. Well, there's the concept of what's called infinitesimal transformations. And this theory was developed by Lie. So these are called Lie groups. And they're continuous groups, not like the groups that we had in abstract algebra. And it also combines topology. Because in the groups itself, because we're going to talk about infinitesimal, we're actually talking about objects being close to each other. If you mention the word close, the next thing someone will ask you in pure mathematics is, what's the topology? So you need to look at what you mean by continuity and what you mean by closeness. And on top of that, you impose group actions. So how you do this is, in algebra, you have a group. And the group is, you can think of the Rubik's Cube. You have actions on the, rotations on the Rubik's Cube, or you have, I don't know I can't remember what fun things we did back in abstract algebra, but we did some fun stuff. But you just have one group. Now you can have a group that has a parameter inside that group, and that parameter is fluctuating. You're allowed to rotate, and that parameter doesn't have to be just a scalar. It could be an entire vector. And when that parameter is moving, you actually can talk about continuity, right? You can say closeness along that parameter. So intuition behind the continuous group is that a small change in factors, if you recall that a group, the important part of a group is the binary operation, right? A small change in the factors of the binary operation when you're putting them together, it's not a product, but when you're putting them together through the binary operation, if you have a small change in each one of those set pieces, it should translate to a small change in the product. That's what you would mean by continuity in the group. And that's how I wrote it out. So if you have small change in two of the factors, it translates, you don't go too far away from the original product. So it's an infinitesimal change. Just to remind you, the group properties, now the elements of your group are actually functions of a parameter. They're dependent on a parameter. So you have number one is closure, that you can binary operate the two and you stay inside the group. You have associativity. You have that there is an identity element, and you have that every element has an inverse. And if you're taking the comp soon, that might be a good thing to just review. Because I wrote the algebra section. What does that have to do with PDEs? Like I said, Lie started this work at the late 1800s, and hence this is named Lie groups. You have a group of transformations. So you can describe a transformation, and this should be reminiscent of linear algebra, but in linear algebra, you probably thought of it as linear analysis, the way it was taught, but it's linear algebra, so it does have something to do with algebra. So you can express a transformation like this, like the way you did in linear algebra class. You can say, I've got a point, x, y, and I want to transform those 2 points to another point, x1, y1. And there's a transformation that does that, that makes that movement for me. And there, if we have the dependency on a parameter, in this case, they would be dependent on a parameter. We saw specific examples of this parameter A and B and C being moved around. So that's the parameter I'm talking about. So if we take a B that's not equal to A, we can take an x1 and a y1 and transform it to an x2, y2 iteratively. So first of all, we can take x, y, and map it to x1, y1. And then we can take, this is supposed to be x1, y1. Yeah, there's my x1, y1. I have it on the previous slides. So now I have x2 is transformed by another parameter, right? But then I can go back to the original, right, and resubstitute back so that I can, instead of, I can remove the x1, y1 from the formula, and I will get x2, y2 can be expressed as the transformation of the first thing that I moved. So it's like on the Rubik's Cube, you move twice. It's this, you know, moving twice would be one transformation, but it's really a combination of the first applied twice.
We're trying to do some kind of fixed point thing.
No, totally group analysis. So here's my group. These transformations are going to constitute a group if we can get one letter C that will do that. Just like the Rubik's Cube, why you have a group is you only have a few things that you can do, and you're just applying that over and over, right? You're rotating, you're flipping, you're really just rotating in different directions. So in the Rubik's Cube, you can make a group out of that. More formally, we can represent TA sub A as a transformation. That's the first transformation. So T of x, y, should look reminiscent of your linear algebra class, and the little subscript A would show the dependency of the parameter. And TB is another transformation, and TB is mapped to x2, y2. But when you compose it, that's just like rotating twice on the Rubik's Cube. You're doing it twice, right? TA composed with TB gives you a TC, a new transformation.
Are those parameters like the basis of those?
No, it's not.
Okay.
No, those parameters are not the basis. They do have a restriction though. So I'll give you an example. Translations. This is an example of just a translation. So if I translate by any scalar, A, then, so the parameter now would be the reals, right? I can translate by any parameter in the reals. Well, I can take x, y, and map it to x1, y1 by this particular transformation in red. And my x2, y2, well, it's going to be a different parameter that might do that transformation. But when I do the substitution, I get this, that x2 is x, and y2 is y plus a plus b. And so that tells me what my c is. So this is how the phi and the phi, where they come from. My t sub a of xy is this guy. My t sub b, and if I compose the two, I get t sub c. So that group action is the composition. And I think we did something like this in abstract algebra. We had composition was our group action. I think we did it with permutations, right? We were composing them. So it's the same thing here. You take each of those translations, and they're dependent on a parameter, but you're composing them. So that's the group action. Well, what would be the identity? We got closure, because you translate twice, you get a translation, right? Right? That's the inverse. What's the inverse? B minus A. So I got it all. I got closure, inverses, identity, and of course I have, because I'm just adding, I have associativity. Nice, huh? You got a full group. Rotations are also parameterized rotations. So it's not the rotations you saw in Dr. Song's class where it's movement, right? You actually have a parameter involved here. So let's suppose that I have a rotation by A, sine, cos. You've seen this before with the angle. then a different rotation with another angle. Then x2, you can reduce it back by substitution. And then the angle identities that no one remembers unless they're teaching it, you can plug in those angle identities, which I actually gave my pre-calc students, because I said, if I don't remember them, you don't have to, but if I remember it, I'm rattling it off like this, then you have to remember it too. That's my rule of thumb. Because if I remember it, it means I used it somewhere. So that translates to this guy that tells you what your C is, right? You've done it twice, you iterated it twice, and you want that new parameter to be the thing that you ended up with. That's the C. So the C is A plus B. So this only works when it nice smoothly goes and you can take the two compositions and make it into the same type of transformation, with the C being a function of A and B. You can easily express it. In both of these cases, C was A plus B. So find the TA, TB, and TC, and find the identity inverse of that group. The transformations are what makes the group. So in order to obtain the group, there must always be an E. A TE is the identity. We also have to have inverses. So that means for each A, there's got to be a B, a parameter B, such that you can turn it around and get back to the identity. We also have a topology, since phi and psi are supposed to be continuous on A. Remember that in the little calculations I did earlier, I was using epsilon, and in analysis class, epsilon's always a small thing. So for sufficiently small changes epsilon, recall that I used epsilon, x and y have to be changed in a small way. So if you go back to the examples I gave you earlier, that if I had small changes in this transformation, it would indeed make only a small change on my original x1, y1, or my xy. Geometrically, it will transform xy to points on a curve called the path curve of the group. Right? Because you're actually acting on, you don't have just the group, you also have this parameter. So as you're working on this parameter, you can talk about the group on that, acting along that parameter. And so that's what we call the path curve. Leave under my door, just hang on to it if you want to. So what I want to do is I want to finish this, I want to show you the Lie group infinitesimal transformations. It gets really messy, but it's a formula for how to generate the entire invariant group for a particular PDE. And there's times when you do this process that you don't end up with anything, so there might be no invariance at all, but it looks for those symmetrical structures in a very systematic way. And then after that, I'm kind of between doing some analysis or going into digging at my semi-group theory book. A semi-group would be one that doesn't have the full group. So you have the identity, and you have the closure, and you have the associativity, but you don't have the inverses. So you have half the group. And that's very important for the heat equation.